Welcome back everyone to section number 7. Here in our second video, we're going to be talking about speed, right? So we want to be able to identify when is something speeding up, when is something slowing down, and of course, what is this quantity that we're calling speed? So that's going to be the objective for this video. Let's get to it. Our first definition is for speed, right? Speed is the magnitude of velocity, which you may remember from your favorite physics course. But the idea here is that speed is like velocity, but we don't care about which direction it's going in, right? We only care about the magnitude. And so in this class, basically the direction is given by the plus or the minus sign. Is it going in the positive direction? Is it going in the negative direction? Again, because thank goodness we're not in multivariable calculus yet, right? So, okay, so if you want to strip away this plus or this minus sign, well then the way that you would do this is with an absolute value, right? Because this turns everything into just positive. So speed is often given by the absolute value of velocity. Again, we don't care about if it's going in the positive direction or the negative direction. We're just going to kill off that, whether it's plus or minus, and just talk about the positive number, right? All right, so for an object speeding up, right? So this phrase, speeding up, means that the speed is increasing. Okay, increasing, right? Well, that's saying how it's changing, talking about a rate of change. And so that, a rate of change, is really the derivative, right? So this is saying that if you were to take the derivative of speed, so here's speed, take its derivative, well, you want this to be positive, right? It should be going in this positive direction. It should be increasing. So, okay, already this looks scary, right? Because you're taking the derivative of something with an absolute value. That's not going to be fun. But we'll see how to get around that. Slowing down means that the speed is decreasing, as you would probably expect. And likewise, that means if you take the speed and you see how it's changing, right? So you're looking at its derivative. Well, if the speed is decreasing, that means that its derivative is negative, right? It has this negative slope, the speed's decreasing. And okay, like I said, these are okay definitions, but I'm a little paranoid or a little worried about having to take the derivative of something with an absolute value. That's not going to be fun. We'll see kind of what headaches this causes here in just a second. But in the meantime, let's take a look at this problem. So this is something that we can actually solve using the definitions that we have. So we have this figure, this graph, is given just the velocity, right? So this is not position, but it's actually velocity of a particle moving in a straight line, a nice horizontal coordinate line for t in the closed interval from 0 to 10. So t is 0, t is 10. Again, this is the time right here, and then it's moving back and forth along the horizontal coordinate line. So the question is, when is the particle speeding up and when is the particle slowing down? And so when you have velocity like this, well, it's very easy to get its absolute value, right? You just take everything and you make it positive. So in this case, for instance, down here at time 6, you have that this is negative 2. Well, let's take that negative 2 and make it positive, right? Positive 2. And likewise down here at t equals 7, we have the velocity is negative 4. Let's go ahead and make that positive 4. And likewise at 8, right? Well, we have 0. You can make that the absolute value of 0, but maybe like halfway in between, right? Maybe at like 7.5. At 7.5, the height is negative 2. Let's go ahead and make that positive 2. And so you can see, actually, when you're taking a function like this and you're applying an absolute value, it's just reflecting all the negative parts over this t-axis. So you'll end up getting a graph that looks like this. So I'm going to go ahead and shade in purple here. So these ones are all fine. These are already positive right here. 0's okay. Again, this is already positive, so the absolute value won't affect it at all. So now this right here is the absolute value of velocity. That's my speed graph. So everywhere you see purple, that's my speed graph. And again, we want to know, when is the particle speeding up, right? So when is this increasing? aka, when does it have a positive derivative? So a positive derivative. Okay, let's move along here. I'm on my purple graph, my speed graph. So I'm moving along here. Okay, the derivative here is equal to 0. Then from 3 to 4, it's negative. Nope. From 4 to 5, it's equal to 0 again. From 5 to 7, looky there, right? So the derivative of the speed, right? So this is the speed graph. Its derivative, aka slope, is positive from 5 to 7. So I like 5 to 7. Let's make sure there's nothing else, right? So, okay, 7 to 8, nope, that's negative. But again, 8 to 10, we should include that as well. So I'm going to do a union with the interval 8 to 10. So right here, this is my answer. When is the particle speeding up? Likewise, when is the particle slowing down? Well, that's going to be when is the derivative of this thing, right? We're thinking about slope now. When is that slope negative? Well, the first place that I see is probably between 3 and 4 here, right? So between 3 and 4, the slope is negative, right? So aka the derivative is negative. So that's where it would be slowing down. Likewise, let's see here, between 7 and 8, we also have that the derivative is negative. It's slowing down, and then as we continue, it looks like it's positive. So these are the places where we have the particle is slowing down. So the claim is when you're given a graph of velocity, right, talking about when is a particle speeding up or when is it slowing down, right, these are okay to do, via a graph, because I can graph pretty quickly here the speed graph, right, the absolute value of velocity. But as I mentioned right here, right, sometimes these definitions are horrible to use. So I'd like to consider the following problem. We won't actually solve it all the way out, but just see kind of how it goes bad. So here's my velocity. If I want to talk about speed, well, then I'm talking about the absolute value of velocity. And that's going to be equal to the absolute value of 1 minus t squared divided by 1 plus t squared quantity squared, all inside of my absolute values. So now this is the thing that I want to take the derivative of and figure out when is that positive and when is that negative. And again, having these absolute values, I mean, it's not impossible. We can figure out a way to work around this, but it is very difficult. So I'm going to give us another way to solve a problem like this. Right, as I say down here, right, something like this that makes us say, makes us pretend like we're on an infomercial saying there's got to be a better way, right? And the claim is there is. We won't have to take a derivative of something so horrible with these absolute values. Let me show you how. All right, so this theorem is what's going to come in and save the day for us. So suppose we have time t, object's velocity is given by v of t, and I'm going to talk about the acceleration, right? So in order to do this, we need to talk about the acceleration. And so the first thing is that if you have the acceleration at some time, I'm going to say time t sub 1 here, is equal to 0, and this can be for any time t1, then the claim is that it's neither speeding up nor slowing down at the specific time, right? So the acceleration is 0, it's not going up or down, there you go. However, if the acceleration and the velocity have the same sign, so that is they're either both positive or they're both negative, right? But if the acceleration and the velocity have the same sign at some time, t1, then the object is speeding up. If, however, the acceleration and the velocity don't have the same sign, okay, they have different signs, so one's negative, one's positive sort of deal, then the object is slowing down at this time. And before we jump into a problem, let's go ahead and think about this logically, right? So if I have a positive velocity and it's increasing, right? The acceleration is positive, right? The acceleration is the derivative of velocity. So, okay, positive velocity and it's increasing, then yeah, that kind of means it's speeding up. Likewise, though, if my velocity is negative and the acceleration is negative, right? That means that it's decreasing. Something like it goes from negative 10 meters per second to negative 11 meters per second to to negative 12 meters per second, right? That means it's also speeding up, but in that negative direction. So you can kind of see that logically this makes sense, that if both the velocity and the acceleration have the same sign, the particle or whatever, the object is going to be speeding up, and likewise if they have different signs, it's going to be slowing down, right? There's a mismatch. All right, let's get a little bit of practice using this theorem in this example, and then the claim is, well, we'll actually go back and solve this example that we held off on. All right, so in this case, I want to calculate out both velocity and acceleration in order to use this theorem, right? Again, my question is, we have a nice particle, we have position, and I want to know when is the particle slowing down. So likewise, I could ask, when is this particle speeding up, right? And so let's get practice using this theorem. So I'm going to go ahead, first of all, calculate out the velocity, because I noticed that it's just position given to me. So I get 3t squared over 3 minus 6t plus 5. And so we can see here the 3 and the 3 kind of cancel out very nicely. And so we have t squared minus 6t plus 5. Okay, how about the acceleration? So I can calculate out the acceleration here. This is going to be 2t minus 6. And again, we're only considering when t is positive in this case. And so now it's my goal to figure out what are the signs on each one of these intervals. So for instance, maybe I'm going to go ahead and map stuff about the acceleration here. Remember, I'm only going down to 0 and then everything positive. I want to know when is the acceleration positive, when is the acceleration negative, right? Because I got to figure out something about its sign. Well, in order to kind of figure out when is it positive or when is it negative, as we talked about in our last video, it really helps to know when is the acceleration 0 or undefined. And well, it's never undefined, right? Because you're not dividing by 0 anywhere. You don't have any square roots. So the question becomes, how can I make the acceleration equal to 0? And so, okay, we have 0 is equal to 2t minus 6. And this is going to give us 6 is equal to 2t, so t is equal to 3. So at time 3, the acceleration is equal to 0. So I'm going to go ahead and split this up and say from 0 to 3, there's one interval, and then 3 and bigger, there's another interval. Let me go ahead and choose test points. So maybe something like 1 here and 4 here, but again, you can choose really any numbers that you like. And if I plug those into the acceleration, so let me go ahead and plug in 1, I'm going to have 2 minus 6, that's going to be 4, and that's certainly a negative number. So the sign, right, we have a minus sign. How about 4? 2 times 4 would be 8, minus 6, that's going to be 2, and that's certainly positive. So this is saying on the interval from 0 to 3, the acceleration is negative, and the interval from 3 and bigger, all the way to infinity, the acceleration is positive. So now I know something about the signs for acceleration. Let me play the same game here for velocity, right? So I'm going to go ahead and draw another number line. In fact, I'm going to draw the number line for velocity right above this one. This will be useful here in just a second. We'll see. So this will be for velocity. Maybe let me go ahead and mark these things. This was for my acceleration down here. This is for my velocity up here, just so we can keep them straight. All right, and just as before, what really helps to know when is this thing equal to 0, and then I can map its signs. Right, so okay, when is velocity equal to 0? That's going to be 0 is equal to t squared minus 6t plus 5, and I see I have a nice quadratic here, so maybe I can factor this thing. And indeed I can, right? I'm going to have t minus 5 and t minus 1. So that says that it's equal to 0 at either t equals 5 or t equals 1. So this tells me how to split up my interval. So right, I'm going to go ahead and split it up here at 1 and then here later at 5. So somewhere over here. Okay, so let me go ahead and choose test points as before. So this is a little bit nasty because there's no nice integer between 0 and 1. So I'm going to just choose 0.5 or 1/2 if you'd like. And then between 1 and 5, I'll choose the test point 2. And then between 5 and infinity, right, 5 and bigger, I'll choose the test point 6. All right, so let me go ahead and calculate out the velocity at each one of these test points. All right, v of 0.5. Remember, I'm using my velocity equation. That's right here. So 0.5 squared, that's going to be 0.25. That's a quarter. Minus 6 times a half, right, 0.5. That's going to be minus 3 plus 5. And again, I really don't care about what the answer is here. I only care about is it positive or negative. And so I can see we're going to have, certainly it's positive, right? It's going to be 2.25. So in this case, we have positive. All right, what about if I plug in 2 as my next test point? So the velocity at 2, that's going to give me 4 minus 12 plus 5. And so I'm going to have 9 minus 12, that's negative 3. That's certainly negative. So between 1 and 5, it's going to be negative. And then finally 5 and bigger, I chose the test point 6, but you could choose 10, a million, whatever. Right? So the velocity at 6, we're going to have 36 minus 36 plus 5. So that's going to be positive. All right, and so let's see when these things have different signs, right? Because we want to know when is the particle slowing down. That means that they should have different signs. Well, you can see kind of here after 5, they have, both of them are positive. But between 5 and 3 here, we can see that the velocity is negative, and yet the acceleration is positive. So this is kind of where kind of lining them up right on top of each other is very useful. Again, we can see the velocity is negative, the acceleration is positive, so they have different signs between 3 and 5. Likewise, between 1 and 3, they're actually both negative. That's okay. But between 0 and 1, they have different signs, right? Again, the velocity is positive in this case, and the acceleration is negative. So again, when is the particle slowing down? Well, that's going to be between 0 and 1, and then again between 3 and 5. So that is my solution. And better yet, let's see, it doesn't seem like we have units at all, right? So there's no seconds or minutes or anything like this. But again, look for units. If you can include those, that's the best. Okay, so this is how we can use Theorem 7.10. Now let's go ahead and tackle this last one, right? So I've given us one more piece of information to make it a little bit easier on us, right? So we have velocity given by this, and I've also specified the acceleration. I mean, we could take the derivative of this using the good old quotient rule and calculate it out, but I figured to save us a little bit of time. So the question now, when is the particle speeding up? Again, I only care about when t is greater than or equal to 0. So speeding up means that they should have the same sign. So again, if I went ahead and I drew out some number lines here, maybe this one will be for my velocity. So this would be v of t. Then I'll also draw one out for acceleration. And I'll draw them right on top of each other just so I can see when they have the same sign and when they have different signs. Okay, now I need to figure out how to break up these number lines, right? And that's going to be, well, when is the velocity equal to 0 or undefined? And likewise, when is the acceleration equal to 0 or undefined? And well, you can say here that there's no way that this is going to be undefined because t squared is a positive number, at worst case 0. Then you're going to add 1 to it, and then you're going to square it again, right? So there's no way that this is going to be equal to 0. It's going to be strictly positive. So the only case that we have to consider is when is the velocity equal to 0? So we're going to set velocity equal to 0. Well, that's going to be 1 minus t squared over 1 plus t squared quantity squared. When is that equal to 0? And in fact, sometimes you may see later on that I just kind of skip this step and I go right to 1 minus t squared is equal to 0, right? So you kind of multiply through by this denominator on both sides, and really 0 times anything is 0. Another way to say this is the only way you can make a fraction equal to 0 is if the numerator is equal to 0, right? So this ends up being the numerator equal to 0. All right, so this gives me 1 is equal to t squared, so that means t should be either plus or minus 1. But in this case, because t is greater than 0, well, we don't have to consider the negative case. So t equaling 1 is the place where I should break this up. So okay, at t equals 1, that's how I should break up the velocities interval. And now I could choose test points, right? So again, maybe I could choose something like 0.5 here, and I could choose something like 2 over here. But I could also choose 3, 5, 100, right? Any test point that you want. All right, so let's go ahead and plug these into our velocities. So velocity of 0.5. So, okay, 1 minus 0.5 squared. So 1 minus, and remember 0.5, that's going to be a quarter, 0.25. And then in the denominator, we have 1 plus 0.5 squared, so that's going to be 0.25, all being squared. And again, I really don't care about what this number ends up being. I only care about is it positive or negative. And so we'll notice that in the numerator, this is going to be positive. And in the denominator, well, you're going to have 1.25 squared. That's also going to be positive. So you're going to have positive divided by positive. So therefore, on this interval, the velocity is going to be positive. Next up, if we do the velocity at 2, right, this is the test point 2, let's see, I'm going to have 1 minus 4 divided by, let's see, 1 plus 4 is going to be 5 squared. And again, the big thing is really the sign here. So 1 minus 4, that's going to be negative, divided by 5 squared, that's going to be 25. Again, all we care about is that it's positive. So we're going to have a negative divided by a positive, that's going to be negative. All right, so now I know about the signs for velocity. What about the signs for acceleration? So, okay, the first thing is how do I break up this interval, right? So, okay, when is the acceleration equal to 0 or undefined? Again, it can never be undefined in this case. The only hope is, right, you're never dividing by 0, that is. The only hope for kind of these breakpoints, how to break up this interval, is when it's equal to 0. So again, this is a fraction. The only way you're going to get a fraction equal to 0 is if you have the numerator equal to 0. So I'm just going to set it up when is the numerator equal to 0, but you can also follow these steps right here, right? You would just multiply through by the denominator, and then you would get the same point that I'm at now. All right, so taking a look at this, well, there's a couple things that can happen. If t was equal to 0, then this entire thing would be equal to 0. Or if t squared minus 3 was equal to 0, this entire thing would be equal to 0. We'll notice again that t should be greater than 0, so we don't have to consider this one at all. So, okay, let's rearrange this, and I get t squared is equal to 3. So that means that t should be equal to plus or minus root 3. And again, because t is greater than 0, I'm not considering the negative case right now. So just positive root 3. So positive root 3, remember this is somewhere between 1 and 2. It's right around 1.7-ish. So I'm going to go ahead and put root 3 right over here. All right, so now I need to choose some test points. Let me choose 1 over here, and I can choose 2 over here. But if you're at all nervous, you know, where is this root 3? You could choose 3 or 4 or 5 or 10 or a million, right? Any test point works. All right, so let's go ahead and plug these into our acceleration. So a of 1. And when I plug that in, let's see, I have 2 times 1 squared minus 3. So that's going to be negative 2 divided by 1 plus 1 squared. So that's going to be 2 cubed. So it looks like in my numerator, I'm going to have negative. In my denominator, I'm going to have positive. So a negative divided by a positive will be negative. Next test point, a of 2. So let's see, I'm going to have 2 times 2 is 4, and then 4 minus 3 will be 1, divided by, let's see, 1 plus 4 is going to be 5 cubed. Again, I really don't care what these evaluate out to, it's just positive over positive. That's the bit that I need to see that this is going to be positive. So the question is, when is the particle speeding up? Well, notice here we have kind of a mismatch, right? Between 0 and 1, we have a mismatch. We have plus, minus down here. But between 1 and root 3, in this case, both of these have negatives, right? So the velocity is negative and the acceleration is negative. So they have the same sign. So there it's speeding up. And then kind of after that, kind of forevermore, we have the acceleration is positive and the velocity is negative. So that's, again, a mismatch. That's going to be the particle slowing down. So the only place the particle is speeding up is between 1 and root 3. And so this is a great technique because, again, we've kind of avoided having to take the derivative of something with an absolute value. All right, well, that is it for this video. Go ahead, take a quick break. Make sure you're trying your homework problems. I'll see you guys next time.